Hello there, my friends, my little cool beans. We are here to talk about classical mechanics and kind of like probably where you will start your studies in A level physics. Alright, so before we drill in to the nitty gritty, I kind of like want to zoom out and give you a big picture view about how all these things come together lah. Because you tend to study physics and have all the subtopics be separated and kind of don't really know how they're related. Well, this is a big picture of classical mechanics. But before I talk about classical mechanics, especially if you intend to do engineering, this is where you stay lah, and you just stay there. Okay, but if you are interested in thinking about physics as more than classical mechanics, then you can see that actually in physics, right, we tend to have four fields, and 95% of your syllabus is inside classical mechanics because we will study things that are traveling at less than the speed of light and are a lot more larger than 10 to the negative 9 meter. So hopefully you have already covered chapter 1 and 2. You're already estimating stuff already. So you can see that 10 to the negative 9 is actually smaller than an atom. So anything that is around the size of an atom and travels slower than the speed of light is well within the classical mechanics realm. Now things becomes very weird when they are very, very small. For example, quarks. Okay, so we'll look at quarks at the end of your AS syllabus, and it also becomes really, really weird when it travels really fast, like around the speed of light. This one here. This is what we call a theory of relativity, which is where our good friend, or rather the smart guy with the weird hair, Einstein, is, where you can bend the nature of space and time. So I'll roughly talk about all of this if it's relevant or if it props up, but we will spend most of our time here, around 95%, and 5% just roughly getting to know the other boxes or branches of physics. But think about it this way. All these three, right, is kind of like where the boundary of human knowledge is. Okay, so a lot of research are still currently being done within these three fields, and if you're interested in doing more physics after this in universities, your lecturers are more than happy to help you on your way. But let us get our basics in place first, and we're going to look at classical mechanics. So classical mechanics, right, we're going to start off with kinematics. So when you look at the term kinematics, right, you can think about it as kinetics, but the mathematics of kinetics. But whenever you see this kind of ICS, right? ICS, physics, mathematics, all these cannot memorize one. There are laws, there are the reason why certain things are the way they are, and we will study them, we will try to explain them, but we will not memorize them without understanding where and what we are trying to memorize. If you want to use that M word, which I'm trying not to use that much, you have a bad memorizing habit. Okay, so kinematics, we're going to start off in this chapter where we talk about how objects move. Okay, so let's say, for example, you were to have a object that is moving. We want to be able to actually have the correct words to describe and also to predict how something moves. For example, I'm sure you've seen this dinosaur. Is it will run around and then it will jump at appropriate times. So if we want to describe the movement of this dinosaur, there are a lot of words that we can use, but we also need to think about the perspective of the game designer. Now when he or she designed this game, right, which I'm playing live now, by the way, if I look a bit distracted, you will need to, there we go, you will need to think about how on earth did they come up with the game mechanics. Okay, which means, right, we need to be able to describe and code how the dinosaur move. Is it going to move faster and faster? If you play the game before, you will know it will move faster over time. How is it going to jump? Where are the position of the cacti, the cactus? Okay, later there will be a bird flying over. How do we describe the velocity of the bird? How fast the bird is flying? How fast is the dinosaur running? So we need a lot of language around this, which is the entirety of chapter 3. And then in chapter 4 and 5, we're going to move on and talk about dynamics and statics, okay? Which is, since we already are able to describe how something moves, we want to be able to explain why it moves that way, because description is not enough, explanation is preferred, okay? And then when we have sat in this for a little bit, we will take a detour into electricity, and electricity is kind of like part of here, but not really. Because if you think about this, right, when we study about the relationship between motion and its causes, forces and torque, we will eventually encounter this thing called energy. Okay, so it is useful to think about circuits in the form of energy, because circuits is just us harnessing the tendency of electrons to make it our slaves. We enslave the electrons in the circuit so they can carry energy for us. So that would be this part, okay? And we're going to move on later, and then we'll talk a lot about pressure, temperature, because one particle is not enough. If you look about gas particles, you have many particles moving together. That's why this is called statistical mechanics, because we need statistics to treat a large sample size of data. If you do maths, you know what I'm talking about. So we'll touch a little bit about this in A2. The continuum part, this too, we will have to leave it into university, because sometimes we will use this continuum, for example, plasticity, fluid, even traffic flow is a continuum, okay? And also we can apply all our understanding of how the world works around us into different fields, like astrophysics, robotics, biomechanics. How do we move for good posture? How do we design things so that it's easy for our human body to use? Construction, etc., etc. And of course, let's not forget gaming, so that if we were to code this, the mechanics is believable lah. You want to play a game where it really feels like you're playing a game, not some weird sim. Okay, especially if gameplay now is almost real. Look at the surrounding. All right. So without further ado, we will begin now. That's a long intro. All right. You can find this in your notes, page 1, chapter 3. We're going to start off by talking about equation of motions, but before that, kinematics, as mentioned before, is a branch of mechanics that describe and predicts the motion of the body without considering the forces that causes the motion just yet. All right, and we are going to go through some key definitions, because look, without definition in science, no one knows what you're talking about, okay? So we gotta make sure everyone is on the same page, so we define things all in the beginning. It's a bit like writing a law document lah. All right. Anyway, if we say describe and predict, right, we basically have a few different tools. Now I know that some of you have your preferences, especially if you are doing double maths, right? Your preferences is probably towards equations and calculation. But think about it this way: to conquer this topic, one skill is not enough. You need to have all three. Unless you are very lucky lah, the one that you like will come out. But how do you know? You do not know, okay? So these are all useful tools or things that you should know. Sometimes we use words to define and to describe. Sometimes there will be some form of equations or calculation. And sometimes we can use graphing to help us solve the question. It really depends on what the question wants. So it is hoped that at the end of the chapter, you will have sufficient confidence in using these three things to answer questions. So let us begin. So the first definition we need to look at is distance and displacement. So distance here is defined as the total path length traveled by an object. Okay, the keyword here is total path length. So that would be the scalar quantity. Unit here is meter. All right, and displacement, which is the more important one, is given the symbol S or X. Okay, and it is the shortest distance between the starting point and the end point of an object lah. Okay, and this is a vector quantity. The unit will be the same as well. So the thing about distance and displacement, right, is that this answers the question when something is moving, right? When we put the cactus inside our dinosaur game, we want to know where to put. Positional statement. So position statement is related to displacement and distance. So if, let's say, for example, I start from my house and I end up in MCKL, so I would like to know how far I have driven. Like my car will register the distance. Okay, if I want to measure a displacement, then I need to go on Google Map, take a ruler, and join my house to MCKL in a straight line. Okay, so one is vector, one is scalar. So I hope you remember vector has both magnitude and direction, and scalar does not. Alright, so let me adjust the size so that it looks bigger. Okay, so yeah, no lah, I shall not adjust now. Recording is happening. Let us continue. This is positional. It answers the question, where's the object now? Now here meaning at whatever time we're talking about. So the next one would be, how fast is the object actually moving? So to describe this properly, there are two things to talk about. One will be speed, which is distance over time. This is not new to you. Distance over time, sometimes we look for instantaneous speed, which is distance over time, sometimes average speed, which is the total distance over the total time taken to travel that distance. Okay, this is as usual a scalar quantity because it's distance over time, so the unit is meter per second. And I kind of like want to highlight that if you have a speedometer in your car, your speedometer registers the speed, not the velocity. It's not a velocity meter, because if you have a velocity meter, then your velocity meter need to tell you the direction, so it will be very complicated, that meter on your dashboard. You'll be a pilot. Okay, so velocity here is defined as rate of change of displacement, and I feel an obligation to pause here and tell you that this is the official definition. I will accept no other definition when you are asked to answer this in paper 2, because there are certain years that accept velocity as change of displacement per unit time. Ladies and gentlemen, you are in A levels. Time to level up. Okay, so definition here is rate of change. It is dv dt. It also helps you remember important properties about the graph. All right, so the rate of change of displacement, and this one, okay, we can equate it to ds dt, displacement being s, which is also coincidentally the gradient of the st graph. This is a really important must know fact. Okay, and this has to do with the instantaneous velocity. So sometimes if we want to look at average velocity, then we will take the total displacement divided by the total time. And my friends, this one no need to memorize. The idea here is, how is my displacement changing over time? Okay, so because of this, that would be called velocity because it depends on how fast you are moving on. All right. So this is as usual a vector quantity. Since displacement is a vector, unit will be meter per second. Alright, and I think this one will talk about how fast are you moving, you here being the object, or how quickly or how is your displacement changing over time. Alright, your position changing over time. Okay, alright, so we will go more into it later. And now we're going to level up some more and talk about acceleration, because our velocity does not stay the same. In A levels, your velocity doesn't always stay the same. That's why if the velocity change, we call it acceleration. So it is useful to think about acceleration like the accelerometer on your car, but it is not because your car is always moving faster and faster. Not necessarily. As long as there is a change of velocity, then there is acceleration. As long as your velocity change, I don't care whether increase, decrease, change direction, doesn't matter. As long as your velocity change, you are accelerating, full stop. And I will not use the word decelerate when I talk about this, because it creates a misconception in your brain where you think accelerate means velocity increase, but decelerate means velocity decrease. Not necessary. Need to read the question. Okay, so learn to use acceleration as change in velocity or rate of change of velocity. Okay, so now we're gonna continue. Alright, so we can write this A as dv dt, which is the gradient of the vt graph. And if you want to look for average acceleration, you will once again take the total change, which is just the initial minus the final, my final minus the initial, divide by the time taken to make that change. Okay, so this rate of change of velocity, by the way, is I'm trying to answer how is the velocity changing over time. Is it changing? If it's changing, then there will be some form of acceleration. Okay, so as usual, this is a vector, meter per second square, because you divide by time or you differentiate against with respect to time again. Alright, so right now we have these three friends, which is pretty important in your life, S, V, and A. Okay, and they are related to each other very closely by first order derivative. Okay, basically, since V is ds dt, the gradient of your S graph will give your V, and A is dv dt, so the gradient of your V graph will give your A. Okay, and if we go in one direction is gradient, you go back is area. This should not be new to you, only the derivative is new. Okay, whether you come from IGCSE or SPM, this idea is not new to you, because from the S, if we look at the gradient of the S graph, we can deduce how the V graph look like. If we look at the gradient of the V graph, we can deduce how the acceleration graph look like. If we want to find displacement from the V graph, we will look for its area. If the red arrow is differentiate, then the green arrow is integrate law, and integrate is look for area what? Okay, so that's all about the definition. So we're gonna talk about an example soon. Alright. But before that, just to remember the unit, whenever we level up or differentiate, it is divided by second. So m, ms negative 1, and ms negative 2, respectively. Okay, we are now ready to talk about an example. You can find this ON 13 paper 2-3 in page 30. I think this is page 32. There we go. Alright, so define velocity, rate of change of displacement. Define acceleration, rate of change of velocity. Okay, this is a not that difficult question. But here you are given a car traveling along a straight road, and you can see that you are given a displacement against time graph. Describe qualitatively. Qualitatively here means use your words. The velocity of the car during the first 6 seconds. Give reasons for your answer. Well, my friend, to give reasons for this, right? Before that, we need to check the gradient, because gradient is related to velocity one. Alright, so let's zoom in and check it out. You can see from this graph, the gradient is fairly constant when the value of t is small, and then after a while it is not constant anymore because I drew a straight line. And then you notice that at the end of the motion, it is somewhat constant as well. The only part that is not constant is the middle portion lah. Okay, so I'm just going to label off that part for you here, and you can see, how do I know? So in real life, when you're doing this paper in the exam, constant gradient here of your xt graph means that this is constant velocity. Use a ruler lah, okay? You can tell when the curve leaves the ruler. So from here to here, the same thing happens as well. You can see that the graph is somewhat a straight line, so here you will have constant gradient, which is constant velocity. So initial and final velocity is the same, only the middle portion here that I highlight. This part look like curve only. Okay, so this part here, I can say that, hey, the curve is getting less and less steep, right? Because it's getting less and less steep, this is a decreasing gradient, meaning this is a decreasing velocity. So this is what I mean by you can find information about velocity from the gradient of this graph. Velocity is the gradient function. Okay, so we continue now. So to describe qualitatively, you can describe chunk by chunk. I will start by writing about the blue part, which is the initial constant velocity. Alright, so I will say something along the lines where you see this part here, the velocity is constant. So I'll say the initial velocity is constant since the gradient of the graph from t is equal to 0 to t is equal to 2 seconds is constant. Alright? Okay, moving on. Then you can see for the center part, right? the middle portion, the middle section. If you want, you can say roughly from 2 seconds to, I don't know, about 3.5-ish. The actual statement of time is not needed. You can say the middle section. That's okay. The gradient of the graph is decreasing, and hence the velocity is decreasing. 1 mark. Last mark, final velocity. So for the last section, 3.5 seconds to 6 seconds, so I can say that the gradient is constant, and because of this, the velocity is constant as well, right? So I can say, but I have to mention that it is smaller than the initial value, because that last mark is a little bit harder to get. Smaller than the initial value because the graph is steeper in the beginning and less steep towards the end lah. Alright, that is the first part. Second part of the question. Calculate a bunch of averages starting with average velocity during the time interval 1 to 1.5 seconds. Well, that's not a problem because 1 to 1.5 seconds is actually a constant velocity, so we're looking for the gradient of the blue line. So I'm going to quickly just draw up to 1.5. Okay, so they want average, or even if it's not a straight line, you can just take the value and ratio. Okay, anyway, this point here is 1.5 and the other part there is 45. Alright, so 45 and 1.5. That, my friends, will give you something like 45 minus 0 over 1.5 minus 0, which is around 30 meters per second. 1 mark, very easy. Show the average acceleration is this. So to find the average acceleration, I'll take the change in velocity over change in time. I know that in the beginning, the initial velocity is 30 meters per second. So I need to find the final velocity, which is the gradient of the red line. My friends, we can draw a triangle and take the rise divide by the fall. Take the height divide by the base lah, okay, of the triangle. So what I normally do is I take the x and y coordinate lah, okay, x1 y1 and x2 y2. So you can see I'm just quickly changing the color. By the way, you can find these notes in your content library, okay? If you don't know where to find, slide into the DM of your teacher lah. They will give it to you. I will give it to you. Alright, so I can see here clearly this 122 on top and around 98 below. Okay, so at 1.5 seconds is 30 meters per second. At 4 seconds is the gradient of the red line. So the average velocity will be 122 minus 98, 6 minus 4 seconds. Okay, so then I will plug in my calculator and I'll get this as 12 meters per second. So to find the change in velocity, I'll take the final 12 minus the initial, which is 30, divided by 4 minus 1.5. That would give me 7.2 meters per second. If you cannot get close to this answer, right, maybe check your calculation. Alright, next part, calculate the average force. I'll just take the mass multiplied by the average acceleration. Okay, I can omit the negative sign because the negative sign here shows us that direction of the force. Alright, next question. This one is also page 33. Define velocity. Wow, right again lah, rate of change of displacement. Distinguish between speed and velocity. Well, speed is a scalar quantity and has magnitude only. Velocity is a vector quantity and has both magnitude and direction. If you don't state scalar and vector, it's not that bad. But if you don't write about the magnitude and direction part, you will not get the mark. Okay?
So next, this one is given a velocity time graph. Previously was a displacement time graph. It's the same car, it's 1005 kg. Well, the brake is being applied. It was time to stop the car, I guess, from 1 second to 3.5 seconds. And right now, you are asked to find the acceleration for the time the brakes is applied, I'm guessing. Okay, now you're asking to find the distance traveled by the car. So to find the distance traveled by the car, right, you will need to look for the area law, which I'm so leisurely shading. Okay, so to look for this area is the only time I will shade. Okay, all right. So now we're going to look for the area of this trapezium, and then I'm the kind of person that cannot cut out the line one. Cannot. Then after that I give up. Alright, so now to find the distance moved by the car during the braking, I'll take the area under the VT graph, and this will be half sum of the parallel lengths 32 plus 18 multiplied by time taken by the height 3.5 minus 1. Okay, do this carefully, okay? You don't want to make this kind of mistake, you will feel very sad. 62.5 meter. So wait a minute, I know people like to jump step, so all the key steps are indicated. If you never show the part where I make the check mark, you might lose a mark. Okay, so next part, calculate the magnitude of the resultant force. To find resultant force or net force, I need MA, so I need to find the acceleration, which is the gradient of the line. So to find the gradient of the line, I will take the change in height, which is 18 minus 32. Okay, because this coordinate is 1.032, that coordinate is 3.518, and then I'll get negative 5.6 meter per second square, the gradient of the line, so that I can just plug into the car, because the car is 1005 kg, negative 5.6, negative 8400 Newton. Why so similar one? Because it's the same sitting. Alright, the negative here shows opposite direction to V. V is always positive, the entire graph is positive, right? So now, it says that the direction of motion here is positive, okay? And you are asked to show with arrows the direction of acceleration, A, and resultant force. So I'm extra, I write the value. You don't have to write the value, but you should follow their sign. So if they use uppercase A, you also use uppercase A and uppercase F. Alright, that would be the second example, and let us look at the final example. This is ON 17 paper 2-1, page 43. This question is very interesting because there are two moving objects. So you have car P and car Q. This is once again the VT graph. Okay, and it says that they travel the same direction along a straight road. The speed limit on the road is 100 km per hour. Stay and explain whether the car Q exceeds the speed limit. Well, we can only compare if the unit is the same. So I'm going to try to convert my kilometer per hour to meter per second. Kilo is 10 to the power of 3 meter per hour. So I have this trick where I write a fraction like this, because when I write a fraction like this, right, I'm multiplying by 1. This 1h over 3600 seconds is essentially 1. So when I multiply this one by 1, what I will get is the same value. So the h and h will cancel out. Okay, so you can see that the kilo is 10 to the power of 3. And when hour cancel out, you are left with the unit that you want, which is meter per second. Okay, so this is meter per second. We can now click your calculator, and I think this is 28. Alright, 28 meter per second. So you can check from the graph above that car Q, this is the speed limit by the way, travels at 30 VU. So car Q, traveling at 30 meters per second, has exceeded the speed limit when t is equal to 12 seconds. So the speed limit is exceeded. Time for assignment. Calculate the acceleration for car P. Very straightforward. Acceleration is once again gradient of the VT graph. So if you look at the VT graph, I'm just going to try to draw a right triangle here, and then see this 24. So I'll take 24 minus 20, which is the height of the triangle, divided by the base of the triangle, which is 12 minus 0. And that would give me 0.333. Do not write your answers in fraction. Never write 1 over 3. So to get the 2 mark, I need to see the gradient, substitution, and then the answer. Determine the distance between the two cars at 12 seconds. Well, that means I need to find the area under both lines. Let's announce that first, and then subtract them. Okay, so car Q looks like a triangle, so I'll take half times the height times the base, which is 180 meters. Car P looks like a trapezium, so I'll take half sum of the parallel lengths, 20 plus 24, and multiply by the height, which is 12. And that would give me 264 meters. So the distance between the cars will be 264 minus 180. They say distance ma, so the direction doesn't matter, 84. But from here, right, you can actually tell that car P is in front of car Q lah, okay? So for t is equal to 12 seconds, from t is equal to 12 seconds, my bad, the velocity of the car remains constant at its value at 12 seconds. Okay, determine the t where Q passes P. So Q will definitely pass P. Why? Because Q is faster. If you look at the graph given, right, the graph given here, okay, because, you know, here you can see Q is traveling faster, because after 12 seconds it maintains the speed. So Q is going to just go up to 30, and then it will stay 30 forever and ever and ever and ever, or until it catches up with car P. Because don't forget, car P is 84 meters in front. Okay, and for car P, it will increase from 28 to 24, and it will stay at 24 forever. Okay, so let's say at some place at the back there, I don't know where, I'm just going to draw a vertical line to denote where that position is. Okay, so that time t, right, is where the car meet, because you know why? If you want to have one car pass the other car, you must be at the same place at the same time, meaning the displacement have to be the same. Okay, so let's say this is time t. Okay, and I need to find the area under both red and green graphs lah. Alright, so I think a good place to start will be SP is equal to SQ. But I already know how far SP travel, which is 180 for the first 12 seconds. So after the first 12 seconds, it will be a red rectangle, so it's 30 times t. And for SQ, it will be 268 plus 24 times t, because there will be the green rectangle. So after that, doing some rearranging and basic mathematics, I will arrive at the answer of 14 seconds. Alright? So that would be the final example for today, and I will see you in the next video. Please do your homework. Bye-bye. Timestamp down below. Not that it matters now, right? Okay, anyway, see ya.